In this video, we're going to discuss section 3.5 from the text entitled Non-Homogeneous Equations and Undetermined Coefficients. So let's step back for a moment and think about where we've been and then talk about where we're going. In section 3.3 and 3.4, we discussed how to solve for the general solution for homogeneous equations with constant coefficients. And so for those, we were setting up our characteristic equation. We were solving for the roots and classifying the roots as real and distinct, real and repeated, or complex. And then we were setting up the solution based on those various classifications. In 3.4, we were talking about different applications, specifically mechanical vibrations, and how we can use those homogeneous differential equations to model those solutions. It's natural in our progression here to now begin discussing how to solve non-homogeneous differential equations. And I want to remind you the difference between a homogeneous DE and a non-homogeneous DE is that on the right-hand side, a homogeneous differential equation has 0. Okay, and on the non-homogeneous differential equation, we have what I'm circling right here, some f of x function on the right. And so we're going to build upon our knowledge of how to solve homogeneous DEs and talk about how that is similar and different from non-homogeneous differential equations. Because these solutions are very tedious and in depth, I'm going to split this section up into 2 separate videos. So this video is going to be part 1. I'm going to cover the first 4 pages of notes, in particular when we're using what I'll refer to as Rule 1, no duplication. In a subsequent video, I will discuss Rule 2, how we solve non-homogeneous differential equations when there is duplication involved. All right, so again, just as a reminder, I have the definition of a non-homogeneous nth order linear equation. The non-homogeneous is referring to the non-zero function f of x on the right. So I'm just going to write non-homogeneous over here. The nth order is coming from the fact that we have an nth derivative. And the linear portion is the fact that each of the y terms and its associated derivatives are linear. Again, this means they're not being squared, they're not being square rooted, there's not a natural log of y or a sine of y. It's just y and its derivatives with no additional functions or power functions being applied. Way back in section 3.2, we were introducing the idea of how to find solutions for non-homogeneous equations. And so what we discussed was if we have a particular solution for the non-homogeneous differential equation, and we have what's called a complementary function for the homogeneous equation. So again, I'm color coding these so that you will associate y sub p with the non-homogeneous and y sub c with the homogeneous. Then we say that the general solution, the general solution of the non-homogeneous equation can be written as the sum of the complementary function and the particular solution. So here's where we're at. Section 3.3 taught us how to find the complementary function. So if we're working with a homogeneous equation, we know that procedure. We set up the characteristic equation, we find the roots, and then we set up the general solution accordingly. That is y sub c. So I am assuming a strong understanding of how to find solutions of homogeneous differential equations. All right, YP is what we're really going to focus on today. How do we find a particular solution to a non-homogeneous differential equation? All right, once we find that, all we're going to do is take the sum of these two. So it's unique in that we're going to be taking a non-homogeneous equation, looking at the associated homogeneous equation to find YC, and then also looking at the f of x portion to find YP. So this brings us into the method of undetermined coefficients. And this is a way of finding this YP particular solution. So it's a way of making an intelligent guess as to the general form of YP for a non-homogeneous nth order linear equation with constant coefficients. All right, so here's the general setup that we'll be using this type of a differential equation. In order to apply this method, the function f of x, again, that's just the function on the right-hand side, must be a linear combination of finite products of polynomials in x, exponential functions e to the rx, and sine and cosine functions cosine of kx and sine of kx. If that function f of x is not a product of those types of functions, so for example, if you see natural logs, or if you see radicals, or any other trig functions outside of sine and cosine, that's beyond the scope of this course, and we're not going to be discussing those. So all of the problems in the textbook will fit this method of having polynomials, exponentials, and sines and cosines. So here again, in this video, we're going to focus on how to solve non-homogeneous DEs that follow Rule 1. So let's read through what Rule 1 says. Suppose that no term appearing in f of x or any of its derivatives, so let me highlight that, f of x or any of its derivatives, satisfies the associated homogeneous equation. So another way to say that is, suppose that no such term occurs as a term in the complementary function. Then take as a trial solution for yp a linear combination of all linearly independent such terms and their derivatives. Finally, determine the coefficients of this trial solution by substituting into the non-homogeneous equation. All right, so essentially what we're doing is the following. We are going to first determine the appropriate terms. And I'm going to write that terms here in quotations. I'm using that in a specific sense. I'm not just saying willy-nilly any terms in the world, but I'm saying those terms that come from f of x and any of its derivatives. All right, so make a list of all of those terms. Next, we want to compare the terms to the complementary function. All right, we want to check and see if any of those terms are duplicated in the complementary function. So compare those terms to the complementary function and check for duplication. And then we have, if there is no duplication, if no such term occurs as a term in the complementary function, then we just want to take as an intelligent guess for our YP a linear combination of the linearly independent terms. So let me go ahead and just emphasize that. We need these terms to be linearly independent. That is part of the rule. So assuming no duplication, check for linear independence. All right, and you could just do that quickly by using the Wronskian as we discussed in the previous sections. And then finally, for your guess, your intelligent guess for YP, your particular solution, you're just going to take a linear combination of all of those linearly independent terms. All right. And then finally, what you want to do here is you want to solve for the coefficients. That linear combination is going to have some coefficients in front, typically A, B, and C. And so next you want to plug YP and its derivatives into the original non-homogeneous DE to solve for those missing coefficients. So that last step there is where the title of this section is coming from. This title was Undetermined Coefficients. So we have to do this extra step here in step 5 to determine those coefficients exactly. All right, so we're going to do a couple of examples illustrating how to go through this process and use rule one, assuming no duplication. And so let's go ahead and move on into the first example, which is problem 6 from the textbook. All right, so we want to find a particular solution of the differential equation. So I want to emphasize here, we're only looking for YP. In this example, we're not, for example, adding it to YC to find the general solution. We're just looking for YP. Okay, so in order to solve for YP, we first need YC. Remember, that's the complementary function, which is the solution to the associated homogeneous equation. We need this because we'll need to look at the terms in the complementary function to check for duplication. So here is the associated homogeneous DE. All I'm going to do is I'm going to drop that x squared term on the right and set it equal to 0. So this is back to section 3.3. How do we solve homogeneous equations? And so what we did is we set up the characteristic equation, 2r squared plus 4r plus 7 equals 0. And then we wanted to identify what types of roots do we get from that characteristic equation. This quadratic doesn't appear to be factorable by hand, so I'm going to go ahead and just dump it into the quadratic formula. Negative b plus or minus radical b squared minus 4ac is going to be 56 all over 2a. All right, so here what I'm getting is a negative 4 plus or minus the square root of negative 40 over 4, which is negative 4 plus or minus. I can factor out a square root of 4, which is 2, square root of negative 10 over 4. And then from here, I can go ahead and simplify this to negative 1 plus or minus 1/2 I square root of 10. So we have now identified that this characteristic equation has complex roots. And so based on that, I can set up my complementary function, notice the subscript c there, as e to the negative x, c1 cosine square root of 10x plus c2 sine square root of 10x. All right, so far we haven't even looked at the non-homogeneous DE. We've only been analyzing the homogeneous DE, but this is absolutely necessary. This is the first step you need to do so that you can refer back to this complementary function. All right, so now I'm going to switch colors here. And now we're going to look at the non-homogeneous DE. So we're coming back to the original. We're coming back to the original DE. 2y double prime plus 4y prime plus 7y equals x squared. And we're going to zero in on our f of x function. F of x is always that non-zero function on the right-hand side. And so what I might do here is I might list all of the derivatives. All right, so the first derivative would be 2x, the second derivative would be 2, and then all subsequent derivatives after that would be 0. So now I want to take a look at each of these terms here in f and the associated derivatives. Now, I want you to recall that we'll be taking a linear combination of the linearly independent terms. So because we're taking a linear combination, I don't care about the coefficients because I'm going to slap an a and b in front. So I'm just going to write a little note here to omit any coefficients from terms. So even though there is a 2x in the derivatives, I don't so much care about the 2, but I care about x. X is different from x squared. So now I'm going to list all of my terms. All right, there was x squared in the original function. Then from my derivatives, I got an x term and I got a constant. Here again, I'm intentionally dropping the 2's because they'll just get absorbed by the constants when I set up a linear combination anyways. And so now I'm going to take a look at this list of terms. I'm going to compare it with the terms that I have in my complementary function. And I can see at a glance that there is no duplication. The terms in the complementary function are e to the x cosine root 10x and e to the negative x sine of root 10x. None of those terms are x squared, x, or 1. So I'm going to just explicitly write out no duplication. If you're one of my students at Western Illinois University, I would like for you to explicitly write this so that I know that you checked for duplication. So just take the 5 seconds and write no duplication. All right, so the next thing I'm going to check for is linear independence. So are these linearly independent? All right, let's do a quick check here with the Wronskian. Remember, the Wronskian is the determinant of the matrix whose first row is a list of the functions. Second row is going to be the first derivative, and then so on and so forth until you get a square matrix. So this one, we only have to go to the second derivative. All right, and then I just want to compute the determinant of this matrix. So I am going to choose to expand along the last column because 2 of my terms are going to be 0. And so I get 1 times the cofactor matrix, if I strike through here, of 2x, 1, 2, and 0. And so this gives me 0 minus 2, which is negative 2. That is not equal to 0, so we can conclude linear independence. All right, so it didn't take too long to check that. So go ahead and just do a quick check to make sure these are linearly independent. At this point, we can now apply rule 1. We checked that we didn't have any duplication in our terms and that our terms are linearly independent. So our intelligent guess for our particular function yp is going to be that yp of x equals, because I already used C1 and C2 in the complementary function, I'm going to use A, B, and C for my particular function. So ax squared plus bx plus c. All right, this is my guess. Now, at the moment, it is possible that maybe A, B, or C, one of them or 2 of them are equal to 0. I don't know the value of A, B, and C. So now in order to solve for those undetermined coefficients, I would like to plug this yp function back into my original dE. So I just want to remind you guys, what is yp? We are assuming that this is a solution to the non-homogeneous differential equation. That's the definition of the particular solution. So if it's a solution to the non-homogeneous dE, that means that I should be able to plug it in and it should satisfy the dE. So when I'm looking back up at my original differential equation, and let me actually recopy it down here, we have 2y double prime plus 4y prime plus 7y equals x squared. When I look at that, I recognize that I need the first and second derivatives in order to plug it in. So let's go ahead and find those first and second derivatives. Yp prime of x is 2ax plus b, and yp double prime of x is just 2a. So now let's substitute this into the original dE. So I'm subbing in yp prime, and yp double prime into the original, again, emphasis on non-homogeneous dE. All right, so let's do it. First, we want 2 times y double prime. So that's 2 times 2a or 4a. Next, I want 4 times y prime. So that's going to give me an 8ax plus a 4b. And then finally, I want 7 times the original yp. So 7ax squared plus 7bx plus 7c. And all of this needs to equal x squared. So what I'm going to do now to solve this one equation with three unknowns is I'm going to collect like terms. So I have 7a of the x squareds. For the linear x terms, I have 8a plus 7b of the x's. And then finally, for the constant terms, I have three of those, 4a plus 4b plus 7c. And all of this equals, I'm going to write the coefficient of 1, x squared. And if you want, you can add the placeholders of 0x plus 0. And now what I'm going to do is I'm going to equate pairwise the coefficients. So let me just color code these. This reduces down to a system of three equations and three unknowns. So for the x squared terms, I get 7a equals 1. For the x terms, I get 8a plus 7b equals 0. And for the linear terms, I have 4a plus 4b plus 7c equals 0. And so now I just want to solve this system, and we can just work from the top down. Here we get that a equals 1/7. If I plug in a here, I get 8/7 plus 7b equals 0. 7b equals negative 8/7. So dividing by 7, I get b equals negative 8/49. And finally, plugging everything into the last equation, I have 4/7 minus 32/49 plus 7c equals 0. And so let's see what I'm going to get here. If I multiply everything through by 49, that might make things a little bit easier. So that's going to give me 28 minus 32 plus 49 times 7, 63, carry the 6, 28, 34, 343. And I dropped my C, so let's add that back in. So I get 343C equals 4, looks like. And so I conclude that C equals 4 over 343. So now we're just going to take our A, our B, and our C, and I'm going to plug it back into way up here, our guess for our particular solution that has A, B, and C. So for our final answer for yp of x, I obtained 1/7 x squared, and technically this is a minus 8 over 49 x plus 4 over 343, and that here is my final answer. Now I will note that the book likes to factor out common coefficients. That's up to you if you want to do that. It's perfectly fine to leave your answer right here. All right, so again, this problem was just focusing on finding the particular solution, which was already an entire page of work, right? These problems are very tedious. The next example wants you to solve the entire problem. So rather than just finding the particular solution, we want to find the solution for the entire non-homogeneous equation. And so I have a little reminder here at the top. If you're solving the entire initial value problem, you need to find your complementary function, your particular solution, which we just practiced here in problem 6, and then you need to add them up. And furthermore, you need to make sure that it satisfies the initial condition. So these problems are so long. And as a result, so that you weren't trying to squeeze everything on one page, you'll notice that here on page 3, I give you the entire page. but I also give you another page just for this one problem. So I just wanted to point that out so that you're not trying to squeeze everything in. You can kind of space out your work here. All right, so we're going to begin this the same way as we did in problem number 6. We need to compute the complementary function first so that we can use that complementary function to check for duplication within our terms. So we are going to consider the associated homogeneous equation y double prime plus 2y prime plus 2y equals 0. And then from here, we're going to factor this to identify the roots. So our characteristic equation is r squared plus 2r plus 2 equals 0. Let's go ahead and throw that into the quadratic formula. Negative b plus or minus radical b squared minus 4ac is going to give me 8 all over 2a. So I have a negative 4 under the square root, which is going to pop out as a 2i. And so we get complex conjugate roots, negative 1 plus or minus I. So as a result, we can set up our complementary function. I get e to the negative x times c1 cosine of x plus c2 sine of x. All right, we don't have anything inside of our sine and cosine functions because the coefficient in front of I is 1. All right, so now we can move on to identifying our terms. So now we're going to consider our function f of x, which equals sine of 3x in this case. What are the derivatives for this function? All right, so let's list a few. The first derivative would be 3 cosine of 3x. The second derivative would be a negative 9 sine of 3x. The third derivative would be a negative 27 cosine of 3x. And if we go once more, it's going to become a positive 27 times 3, 81 sine 3x. And I'm just going to write a dot, 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 because we could play this game forever. But the reality is when I look at this collection of f of x and its derivatives, I'm really only seeing 2 different functions popping up with some different coefficients and plus and minus signs in between. So although I'm going to get different derivatives as long as I do this, since I don't care about the coefficients because I'm taking a linear combination, the only terms that I'm going to consider here are sine of 3x and cosine of 3x. I only get 2 terms in this case. So now I want to look at these terms and I want to compare them to the terms in the complementary function. Do I have duplication? No, I do not. So the terms sine 3x and cosine 3x aren't occurring up there. First of all, we have a cosine of x and a sine of x, so we're missing the 3. And furthermore, they're both being multiplied by e to the negative x. So no duplication here. Go ahead and note that. All right, so this means we can move on with rule 1. Let's go ahead and just check for linear independence. So the Wronskian is going to be just a 2 by 2 in this case. We have sine of 3x, cosine of 3x, and then their derivatives, 3 cosine 3x and negative 3 sine 3x. And we can just compute the derivative of this 2 by 2. This is a negative 3 sine squared 3x minus 3 cosine squared 3x. If I factor a negative 3 out, I have sine squared 3x plus cosine squared 3x. And sine squared plus cosine squared is 1. So this entire Wronskian equals negative 3. which most certainly is not equal to 0. So we have concluded that these terms are linearly independent. So we have met all of the hypotheses to apply Rule 1. And so now for my guess, for my particular solution, I'm going to say I am taking a linear combination of these two terms, and the order in which you set them up is irrelevant. So I'm going to do a sine of 3x plus b cosine of 3x, but you're more than welcome to do a cosine of 3x plus b sine of 3x if you'd like. So now again, remember, what is the particular function? This is a solution to the non-homogeneous differential equation. That means I should be able to plug it into the original non-homogeneous DE to solve for those coefficients A and B. So what was our original DE? It was second order. So I need to compute the first and second derivatives of this particular function. So let's go ahead and do that. The first derivative here is 3a cosine 3x minus 3b sine 3x. And the second derivative is a negative 9a sine 3x minus 9b cosine 3x. All right, so here are all of our derivatives. And now I'm going to plug this into the original. So plug yp, yp prime, and yp double prime into the original DE. So let me go ahead and just recopy that original DE so that we have it here. Y double prime plus 2x prime, or excuse me, not x, let's do y. 2y prime plus 2y equals sine of 3x. All right, so we're plugging in yp prime, and yp double prime into that red differential equation, and let's see what we get back out. I'm going to group these in parentheses just to kind of keep track of where we're at in the DE. So y double prime is a negative 9a sine of 3x minus 9b cosine of 3x. Next, we want 2y prime, so that's a 6a cosine 3x minus a 6b sine 3x. And then finally, I want 2 times the original, so that's a 2a sine of 3x plus 2b cosine of 3x. And all of this needs to equal 1 sine of 3x and 0 cosines of 3x. So I'm just adding that placeholder there of a cosine 3x. And then similar to what we did in the previous example, we were equating coefficients of like terms, namely the x squareds, the x's, and the constants. Here we're just going to equate coefficients of sine of 3x and cosine of 3x. So let me do one step further here to just kind of combine all of the sine functions, and similarly for the cosines. So I have a negative 9a minus 6b plus 2a sine of 3x. And then for the cosines, I have a negative 9b plus 6a plus 2b cosine of 3x. And again, this just equals sine of 3x. I'll just write plus 0. And so let me just combine once more, and then we'll set up our system of equations. I have negative 7a minus 6b of the sines. And I have 6a minus 7b of the cosines. All right, so again, let's just color code so that we're all on the same page here of what is being equated. I'm going to take the coefficients of the sine functions and equate them in green there, and the coefficients of the cosines and equate them in yellow. So I'm just going to move this onto the next page so that we're not cramped for space. So here is the sine of 3x functions. I have negative 7a minus 6b equals 1. And for the cosine of 3x functions, 6a minus 7b equals 0. And then you can choose your favorite way to solve these. You can either do elimination or substitution, or again, if you're familiar with linear algebra and you want to set up the coefficient matrix and let your calculator solve for these, that's fine as well. I would like you to indicate that on your paper whenever you're turning in work so that I can follow how you're solving for these. I'm just going to use substitution here. I will solve for b in this equation. So 6b equals negative 7a plus 1. So b is going to be 1/6 of negative 7a plus 1. And so I will go ahead and plug this into the equation. Oops, and I just noticed I made a sign error, so let's fix that to a minus. Okay, and now I'm going to plug that in right here in the second equation. I'm going to start on the next line. So 6a minus 7/6 of negative 7a minus 1 equals 0. Let's go ahead and distribute here. 6a plus 49/6a plus 7/6 equals 0. I'm going to go ahead and just multiply through by 6 to get rid of the fractions. So 36a plus 49a plus 7 equals 0. So if I combine 49 and 36 is going to give me 85a plus 7 equals 0. And so finally I can solve for a. A is equaling negative 7/85. It's a super gross number, but that's okay. And so now I'm going to plug that back into my expression for b. B equals 1/6 of negative 7 times negative 7/85 minus 1. So that's 1/6 of 49/85 minus 85/85. So what's that going to get me? Let's see, that's a negative 36 over 85. 6 goes into 36 6 times, and so I get negative 6 over 85 for my b value. All right, so let's kind of highlight those. Here's b, here's a, and then I need to go, I'm going to zoom out here for a moment. I need to go way back up here. I want to take those values and go all the way back up here where I had my original guess for YP. So in particular, I'm plugging in for A and B right here. So A is the coefficient of the sine function, B is the coefficient of the cosine function. And let's plug those in. I'll keep it in red because it's important. So Y sub P of X is negative 7 over 85 times sine of 3x minus 6 over 85 cosine of 3x. All right, so here's what we got for our particular solution. And of course, if you want, you could factor out a negative 1/85 to make it look a little bit nicer. We have 7 sine of 3x plus 6 cosine of 3x. All right, now in problem 6 in the last example, we stopped here. We were just looking for the particular function. But now we're looking for the overall solution of the IVP. And so let's get back, well, let's switch it to purple. All right, so now our goal is to come up with the solution y of x, which is the sum of the complementary function plus the particular solution. So we have to go all the way back up to the beginning where we had already found the complementary function. And if you'll recall, that was e to the negative x times c1 cosine of x plus c2 sine of x. So that right there is the complementary function. And then I want to tack on the particular solution. So minus 1/85 sine 7 sine of 3x plus 6 cosine 3x. Now we want the particular solution to the non-homogeneous differential equation that satisfies the initial conditions. So let me remind you of the initial conditions. So the initial conditions were y of 0 equals 2 and y prime of 0 equals 0. We currently have y of x, so let's go ahead and impose that first initial condition. When I plug in 0, all of the sine functions die, and e to the 0 is 1. So what I'm getting here is a c1 times cosine of 0, which is 1, plus 0, minus 1/85 of 0 plus 6. And this equals 2. So in other words, C1 equals 2 plus 6/85. And so if I get a common denominator here of 85, what am I going to get? So 2 times 85 is 170 over 85 plus 6 over 85. So I get my C1 value is 176 over 85. All right, so we're almost home free. The only thing we're missing is C1. And in order to find that, I'm going to need to calculate the first derivative so that I can use that other initial condition. Now, even though I have C1, I'm just going to leave it out for now when I calculate the derivative. So let's find y prime of x. Here, I'm going to have to use the product rule for this first term because I have the exponential and then I have the trig functions. So if I take the derivative of e to the negative x, I get a negative e to the negative x. I'll just rewrite that second function there. And then the second half of the product rule, I will rewrite e to the negative x, and I'm going to take the derivative of everything inside the parentheses. So a negative c1 sine x plus c2 cosine x. All right, and now moving on to the second piece, I'm going to compute its derivative. So I'm going to use the chain rule. It'll pop out a 3. I have a 21 cosine 3x, and that'll actually become negative 18 sine of 3x. All right, that's kind of a bruiser there. But the good news is when I plug in 0 for all of my x's, all the sine functions will die. So I'm just going to cross those out right away. And so now I want to evaluate at 0. I get a negative 1 times C1 plus 0 plus 1 times 0 plus C2 minus 1/85 times 21 minus 0. And all of this needs to equal 0. So let's see what we have. I have a negative C1, which I found C1 to be 176 over 85. So I'm plugging that in now, plus C2 minus 21 over 85 equals 0. So I conclude here that C2 is equal to 176 plus 21 over 85, which is 197. All right, we're finally at the point where we can write out the solution to the IVP. So I am going to take this C1 and C2, and I am going to plug it in right here and here, and that is going to be my final answer. So I'm going to pull this 1/85th all the way out front so that it's not trailing along. And my final answer here is y of x equals. Here's my 1/85th constant out front. Then I have e to the negative x. C1 was a 176 cosine x. C2 was a 197 sine x. So there's that complementary function, and then minus 7 sine of 3x plus 6 cosine 3x, and close those brackets. And that whole thing is the solution to the IVP. That's it. Only took 2 pages, right? All right, so this is going to conclude part 1 of our covering of section 3.5, the non-homogeneous equations and undetermined coefficients. In the second part of this video, we're going to discuss rule 2. So how are we going to handle setting up the guess for the particular solution if we have duplication between the terms and our complementary function? So stay tuned for that upcoming video.